What would happen if a tiny needle or a speck of dust, with almost no mass, hit the Earth at the speed of light? Would it burn up in the atmosphere like a meteorite? Or would it just drop to the ground with a thud? Maybe cause a massive explosion? Could it pass right through the Earth? Could it even destroy the Earth? Let's find out. To understand what a needle traveling at the speed of light, or about 186,000 miles per second, would do to Earth, we first need to tackle a more fundamental question. If you turn on the headlights of a spaceship traveling at 300 miles per second, would the light travel at approximately 186,000 plus 300 miles per second, making it 186,300 miles per second? And what if you turned on the lights of a car moving at the speed of light? Would the light then travel at twice the speed of light? After all, if you throw a ball at 6 miles per hour while standing still, the ball goes 6 miles per hour. But if you throw it forward from a car going 31 miles per hour to you, the ball still seems to leave your hand at 6 miles per hour, but to an outside observer, it would appear to be moving at 37 miles per hour. Because to them, the ball's initial speed isn't 0 but 31 miles per hour, plus the 6 miles per hour you threw it. Now, if you turn on the lights of a car moving at the speed of light, shouldn't an outside observer see the light traveling twice as fast? No. Here are 3 major errors often made in these questions. First, we fail to specify whose perspective we're viewing from. Thanks to the theory of relativity, we understand that events in the universe are not absolute but experienced relatively. So, a ball thrown from a moving car doesn't have an absolute speed in the universe. You see it at one speed, while your friend watching from the road sees it at another. Neither speed is more correct, both are equally valid and real. This is what we call the relativity of simultaneity. The second mistake is thinking that the speed of light is like any other speed. While numbers like 1 or 5 are just numbers, when you use them to denote speed in this universe, they cease to be ordinary numbers. Speed like 1 or 5 miles per second can be added or subtracted in everyday scenarios, but the speed of light, or 186,000 miles per second, isn't something you can add or subtract in the same way due to special effects understood through relativity. It's a speed constant from the fabric of the universe, not something to be exceeded. Moreover, when discussing speeds close to light speed, the math we're familiar with starts to change. For instance, adding 180,000 miles per second to 62,000 miles per second doesn't give you 242,000 miles per second. This is crucial to understand. There's a lot to unpack in what I've said so far, so let's take it slow and break it down. The universe isn't composed of 2 separate structures, space and time, as Newton believed. Space and time are different manifestations of the same structure, and without understanding this, you can't fully grasp motion and speed in the universe. Here's a mind-blowing fact. You feel stationary right now, don't you? That's not the crazy part. Wait for it. Despite feeling still, your speed in the universe is tremendous due to Earth's rotation, its orbit around the Sun, the Sun's movement around our galaxy center, and our galaxy's motion relative to others. But from your own perspective, you're completely motionless. However, that's not true. Right now, you're moving through space-time at the speed of light. Let me explain. Imagine a car that can only go 62 miles per hour, and it can only travel north, east, or between these directions. If you're going directly north, you're not moving east at all, right? If you're going directly east, you're not moving north at all. But if you're heading northeast, your speed is split between north and east, right? You can calculate this with simple high school trigonometry based on the angle of travel. All objects in the universe behave similarly, but instead of north and east, we're talking about space and time. When you start moving, you're transferring some of that speed from time to space, making time pass slower for you. The faster you go in space, the slower you move through time. The slower you go in space, the faster you move through time. As you approach the speed of light, your speed in space increases dramatically, and at the speed of light, time would stop for you. This is mind-blowing because, for example, a photon from 1 billion light-years away takes about 1.3 billion years to reach us, considering cosmic expansion. But for that photon, no time passes at all. From a photon's perspective, everything would seem frozen. Moreover, another prediction of special relativity is that distances in the direction of motion contract, reaching maximum contraction at light speed. Thus, a photon traveling from one end of the universe to the other does so without experiencing any passage of time and with space so contracted that it experiences all 93 billion light-years simultaneously. The speed of light is truly bizarre. Anyway, let's not fry your brain further and get back to the point. For very low speeds, this time dilation, length contraction, or spatial movement is negligible, allowing Newton's physics to make accurate enough predictions. When you add 1 mile per second to 5 miles per second, you get 6 miles per second, just like Newton predicted. But when you add 180,000 miles per second to 62,000 miles per second, you don't get 242,000. If you were to throw an object at the speed of light from something moving at light speed, an outside observer would see it moving at roughly half the speed of light. Crazy, right? But there's one exception to all this: light itself. Since light has no mass, it must always travel at the speed of light. When you turn on a flashlight, the photons don't accelerate to light speed. They're already at light speed the moment they leave the source. Moreover, light must travel at the speed of light for any observer, which is one of the fundamental and unchallenged assumptions of relativity. So, if he turned on the lights of a car moving at light speed, the light would still travel at light speed to you inside the car. To an outside observer, the light and the car would be moving at the same speed, making it seem like the light never leaves the headlights. However, there's another error in this light speed car scenario. Assuming an object with mass could travel at light speed. No object with mass can reach the speed of light because, as we'll see in another video, mass seems to increase as you approach light speed, becoming infinite at light speed. Thus, to push something from just below light speed to light speed would require infinite energy, which doesn't exist in our universe with a known beginning. Hence, no object with mass, including a needle or dust particle, can travel at light speed. Anything moving at light speed must be massless, like photons or gluons, which, as we've discovered, must travel at light speed and only light speed. But let's say our needle is moving at 99% light speed. What happens when it hits Earth? Something extraordinary, a colossal explosion. Time would need to be slowed down significantly to understand what happens. When our needle enters our atmosphere at near light speed, it would experience all atoms in the atmosphere as practically stationary. Normally, if you threw this needle at a regular speed, aerodynamic forces would come into play due to the fast-moving air molecules. But at near light speed, there's no time for these interactions. Instead, each atom hitting the needle's surface gains so much energy that fusion reactions start, with nitrogen, oxygen in the air, and carbon, hydrogen. Oxygen from the needle fusing together. Behind the needle, a near vacuum forms, and during fusion, gamma and X-rays are emitted, exposing everyone nearby to lethal radiation. But there's no need to worry because everything around is about to vaporize anyway. As fusion continues, the atmosphere turns into plasma, and from that point, a fireball expands outward. Sound familiar? It's like a hydrogen bomb. The needle would start to slow down due to these interactions, but this slowdown is so minimal that in our slow motion scenario, it's almost negligible. Within nanoseconds, the needle itself begins to disintegrate due to fusion, with each fragment initiating its own fusion reactions at near light speeds, leading to an area blindingly white with light brighter than hundreds of thousands of suns, followed by an enormous explosion in our atmosphere. Yes, our needle has become death. The explosion is equivalent to a hydrogen bomb. This would be like the largest hydrogen bomb ever detonated on Earth. That's how a tiny needle or a dust particle at near light speeds can unleash such immense energy. This isn't something we encounter in daily life, but by asking these intriguing questions and applying sound physics, we begin to uncover extraordinary truths about the universe. And those who master these truths will shape the future. See you in the next video. Goodbye.